Hello, I'm Yu. I'm pleasant to present our work called Complexity Heuristic KD-trees for neighborhood-based exploration of 3D curves. This is the work from Taiwan's Ideas Lab. Well, volume data is very common in scientific visualization. However, some data like velocity fields, scientists are hard to observe any useful information from a series of numbers. Therefore, streamlines are proposed to depict the motion of materials and visualize the velocity field. Well, people extract lines from the vector field using three methods. After that, we sample along the direction with numerical algorithms. Finally, we get the streamline field. Such a dataset is applied widely in scientific visualization, like in fluid dynamics. However, directly rendering streamline field is not enough. People always suffer difficulties in observing occupied lines, as they can't figure out inner features, especially in intricate streamline fields. Therefore, in scientific field, researchers propose many methods to visualize streamline fields. For example, fiber contraction and streamline abstraction depict the basic shape of complex datasets. Well, researchers also propose a series of methods to fade out lines and show the inner features, which is called opacity optimization. But such applications involve performance issues. Users often need to wait for some minutes or hours before they obtain results. For these applications, one of bottlenecks is nearest curve computation. It requires program to find near curves with specific conditions, like k-nearest point query in point datasets, but we use actually curves instead of points here. To resolve performance issue, we propose an algorithm CCH KD-tree. Our method is able to improve the speed of existing neighborhood search approaches by at least an order of magnitude. In a nutshell, we solve the efficiency issue of nearest curve problems. We propose our new data structure, CCH KD-tree. Well, the motivation of this new algorithm is simple. For data structure, we use KD-tree. Besides, a heuristic method is applied for further optimization. For data structure, we select the KD-tree because it's friendly with low-dimensional data in Euler space. Other methods are better for higher-dimensional data, like variations of KD-trees, LSH, graph-based methods. For our 3D data, these methods yield a higher time complexity or a significant overhead in searching procedure, unless we depict each of our curves as a high-dimensional vector here. Hash is also a good method, but it assumes data are even distributed, which is not friendly for k-nearest problems. Thus, we don't use pure hash to address our problems. For traditional KD-tree, trees are built on point datasets. As for our problems, we need to deal with curves. In streamline field, each line is described by discrete sample points. Thus, we have two approaches. The first approach is simple. We can build a KD-tree with sample points from curves, like this. Each splitting is based on sample points. Another approach is about segments. We can regard each curve as some tiny segments connecting one by one, and then build a KD-tree with segments. For the existing methods, point-based KD-tree is fast but inaccurate, while segment-based KD-tree is slow but accurate. For example, in a PowerPoint, purple points are query points, and the point-based KD-tree will ignore paths between two neighboring points, like the area between two orange sample points. While segment-based KD-tree will notice this. For point-based KD-tree, we use the implementation of LAN as state-of-art, an open-source library for approximate nearest neighbor search. For segment-based KD-tree, we implement a version to validate the accuracy of the algorithm. For heuristic methods, we model after SAH, an algorithm for retracing problems. It evaluates expected intersection computation cost to decide the splitting position and the branch cuts. Well, for the next section, we will introduce some details of our CCH KD-tree. The main idea of our algorithm is to build KD-trees with fitted segments, reducing the number of elements to lower time complexity. In order to fit curves into segments, we need to simplify geometry first, and this is our first step, curve partitioning. Afterwards, during the tree construction, we split curves again and apply our heuristic method, CCH, for branch cutting. Finally, as each curve is divided into several curve segments, we fit them into segments and store to the data structure. The first step is simple. We break down each long curve into short curve segments. Here we use Raman-Douglas Puker to achieve this. Well, in this phase, we only record the candidate points where we might split curves, but not actually to split them, since we might adjust splitting during the KD-tree construction. For example, the S-curve is divided by points P5 and P10, so P5 and P10 are recorded as candidate points here. For the second step, we build a KD-tree based on curve segments. The splitting is simple, just like traditional KD-tree, but we focus on candidate points here, since candidate points are better to represent curve segments. First, we pick a dimension of highest variance, like traditional KD-tree. Then, we divide the data into two pieces by the median position of candidate points. Although sometimes median position is not the best strategy for online query performance, but in most cases, it is close to the best performance with a faster tree construction speed. However, splitting will generate new curve segments in most cases. For instance, this splitting generates 3 extra curve segments. Furthermore, the left subtree has the same quantity of curve segments as its parents. This splitting is even worse than in the search. Therefore, we need to identify inefficient splitting and then discard them. So, how to identify a full-time splitting? Here, we use the heuristic method, CCH. Like SAH, first we evaluate potential search cost, then compare it with brute force. If evaluated search time is higher than in the search, then we discard the splitting and stop further dividing. To evaluate the search time, we calculate the traversal cost and the backtracking cost. Those two costs depend on splitting efficiency in the current node. For traversal cost, it indicates the computation cost during the top-down search process. This is very simple, just compute the expected time of searching 2 subtrees. And for backtracking cost, it indicates the computation cost when we backtrack to other nodes and continue to search. The cost is proportional to the depth of current subtree. Therefore, if the splitting generates lots of extra curve segments in subtrees, the depth of subtree will increase rapidly, cause a significant overhead during backtracking. For traversal cost, before we calculated the expected search time, we first assume queries are even distributed. Thus, the chance to search one side depends on the volume of its node. Unlike SAH uses surface areas to compute the expected search time. Besides, each node is described by AABB, so the volume of node is easy to compute. Note that the AABB does not tightly pack in the elements in the node. It just depicts the boundary of node, but not elements. And after splitting, We also assume we search each node with brute force. Finally, to calculate the expect of computation time, just multiply the probability and element quantity together. Then we will obtain a simple traversal cost. As for backtracking cost, we also simplify a lot. In the previous study, the expected backtracking time is approximately proportional to the tree depth in nearest search problems. Since our partition does not split elements into exact two halves, we need to evaluate the final tree depth of our subtrees. Well, directly simulating the construction process is too consuming, so we assume the splitting efficiency does not change during partitions. In fact, the splitting efficiency will become worse if we go deeper. To evaluate the average depth for each pass, this also involves complex computation. Therefore, we calculate the average fall of minimum and maximum depths here, and then we obtain a quick result of the expected backtracking cost. Finally, we put these costs together. Among these equations, T-dist indicates the cost for each time we calculate the distance between querying points and segments, while T-traversal indicates the cost for iterating through different nodes. We add two costs together with such ways, then compare it to the brute force search, and decide whether we should discard the partition or not. As we finish the construction of KD-tree, it is time for fitting curves. Like previously stated, we mark some sample points as candidates to split the curve. Now, we apply these points and obtain curve segments. For each of them, we fit it into a real segment. Here, we can directly connect the end of curve segment to fit it, which ensures geometric continuity. While fitting curves with PCA will provide a higher accuracy for our nearest curve problem, since PCA is able to find the projection axis with minimal reconstruction error. Once we have built our KD-tree, it is time for query. The query process is the same as traditional KD-tree, except that we have to filter out segments from the same curves with a hash map. For results, we first test our CCH KD-tree on aneurysm datasets with different query problems. The results show that our CCH KD-tree is 1 or 4 times faster than Flame. Furthermore, we test our CCH KD-tree on 10 datasets from different fields and evaluate it with query time, curve recall, and precision. Each dataset contains about 3,000 curves and millions of sample points. It shows that, although we have some tiny accuracy loss, about 0.5%, we boost the algorithm 2 or 5 times for different nearest curve problems with half memory usage, comparing to the Flame. Moreover, if we compare our algorithm with ground truth, it boosts the speed at least 10 times for different query problems, at a cost of 1% recall or precision. Details are listed on the right side. The box plot indicates all 10 datasets' performance on different algorithms. For construction, our methods use less memory because sample points are simplified and only segments are retained in the KD-tree. Also, the construction of KD-tree is fast. It usually takes about 1 second to finish the offline process. Well, we also apply our algorithm to some applications. For example, real-time interaction. This includes point selection, something that requires nearest curve search. And these short videos show some operations related to nearest curve query. Also, there is another example, opacity optimization. It fades out unimportant data, so so that peripheral lines will not occlude inner lines, and users are able to discover inner features, like this. To compute the importance of each line, there exist many methods, like curvature-based or line attribute-based methods. We also propose a method using nearest curve query to calculate importance for each line, to make full use of surrounding information and provide a large-scale structure for users. The result is tagged with similarity in the video. Another application is fiber contraction. In this algorithm, we compute the neighboring relationship between different curves. After that, we move them together to show the abstract of fiber data. This animation shows the process of contraction. Well, this algorithm costs many computation resources. If we use a single thread, the user needs to wait for several hours before they see the results. Here, we use multi-threads and our optimized algorithm. It only takes several minutes to compute that. Our CCH KD-tree boosts the fiber contraction with a tiny visual error. For abstraction, since different algorithms may produce distinct results, a tiny error usually doesn't impact too much, in fact. Overall, our CCH KD-tree boosts nearest curve search at a cost of accuracy. Also, we validate its usage through 3 applications. However, this data structure is still limited for large datasets, like millions of different long curves. Accelerating with GPU is also a potential problem, as tree structure is not friendly to GPU currently. In the future, we might focus on large datasets managed out of core storage for KD-trees. Also, we will explore more neighborhood-based visualization applications. For instance, the nearest samples of different lines might be grouped into the same cluster, and we will thus investigate neighborhood-based spectral clustering for exploring flow data. We acknowledge to Martin Everts, who assists us results for comparison. Also, we acknowledge to Zhang Jian, Sun Yinqi, and Jiang Xiao previous efforts for algorithm design. Thank you for listening.